Good afternoon, everybody, or nobody, or whoever's at the other end of this legacy video. This afternoon, we're going to discuss a little bit about magnetic fields, magnetic forces, and how those two couple with normal matter. Introduce the concept of the auxiliary field, and at the end, we're going to apply all of the above to a neat little problem in Chapter 16 of Griffith's book, Introduction to Electrodynamics. So let's dive right into it. So at this point, I'm going to assume that everyone on the other end has had a little bit of background in physics, in particular has taken University 2 and has an idea of what a magnetic field is and some of the math that's behind expressing a magnetic field. Some key points that every magnetic field, B vector hat, is going to be created by a current. Some amount of charge moving per unit time. There are no magnetic fields without moving charges, and there are no moving charges that are not accompanied by a magnetic field. So that's our first point to touch on. Next point, in regards to fields and matter, we all have the good old-fashioned Bohr model in our heads of what an atom is. Let's take the hydrogen atom. So we're going to put a little proton here, and whizzing around it, we have a little electron here, moving at some speed, v, all the simplicity of a circular orbit and all that fun stuff. However, in the frame of reference of the proton, so that the electron's orbiting around it, we have a charge and it's moving. So this should constitute a current, albeit we would have negative charge rotating this way. It's equally fine, and the convention is to run with the idea that positive current is running in the opposite direction. And so this little guy himself should induce a magnetic field. And as we all know from experience with magnets, and if we bring magnets in close enough to each other and their pole configurations are just so, we'll either see some kind of an attraction and repulsion. Now, if I take this atom and I zoom out a bit, and the current is running in the same direction, this would be clockwise if you're looking down the axis here. This moving current is going to induce what is known as a magnetic dipole. For all that we're interested in is what the magnetic dipole effectively is. I have this little atom with the current moving around this way. It's going to induce a magnetic field such, and by using our good old-fashioned right-hand rule, if the current is moving this way, it's going to induce a magnetic field that's going to be coming out the bottom and into the top. And of course, we'd have all kinds of other field lines coming in. Over here, we'd have some looping and so on and so on. But the thing to point out here is the side of the loop where all the field lines are coming into is effectively a south pole. And the field line, and the side where the field lines are coming out of is effectively a north pole. All right. So if I brought a bar magnet up to this, up to one of these little guys, let me put one over here now. Current moving this way. We'll give the magnetic moment some notation in a vector. You can also think, oops, this is backwards. Oh, let's have the current run this way. Make things easier on myself. It's just a rule of thumb that the magnetic dipole moment, its vector direction, will also be, in my experience, the direction of the effective north pole of this thing. So if I were to come in with a good old bar magnet, then these two should repel each other. And if I come in with a good old bar magnet flipped around, then these two will attract each other. All right. Now, from here, let's get an idea of what a little magnetic dipole would do in the presence of a larger uniform external field. So again, we take our little hydrogen atom. This time the current's going to go this way. It doesn't particularly matter. Just depends on our frame of reference. We'll have a magnetic dipole moment that goes up here. And let's say we apply a uniform magnetic field all in this region coming up in this direction B. Or this direction, and label it B. And the angle between these two vectors is theta. All right. Skipping the boring stuff, because this isn't particularly what we're interested in this afternoon. This configuration would apply a little torque to this moment. It's going to want to, this side will want to rotate this way. This side will want to rotate this way. And again, a rule of thumb is that the magnetic dipole moment is going to want to align itself with the magnetic field. Another interesting point of this that we'll need is that if the magnetic dipole lines up with the field, again, it's going to induce its own magnetic field, and the induced magnetic field, or the magnetic field of the dipole, is going to add to the strength of B. As a side note, it is possible for the magnetic dipole to flip and be anti-parallel to B, in that case reducing the strength of B, but that configuration is unstable, and any little fluctuation, any perturbance away from that position through, let's say, thermal agitation of local atoms is going to throw it back to trying to be parallel. So we can neglect the other case most of the time. So now that we have that under our belts, oh man, let's get an idea of how magnetic field affects matter. If I have just a block of matter and it's filled with little dipole moments and all randomly oriented, as they will be. Again, if you have all these atoms in a material and the material isn't at absolute zero, then it's going to have some thermal agitation, and as the atoms jostle around and bump into each other, it's going to disturb their dipole moments and on average orient them randomly. Now if I apply a magnetic field, an external magnetic field, I'll call it B naught, then the net effect of this is to try to get these little dipole moments to align themselves, or align with the magnetic field. So you might get something like this. You might still have a couple that don't want to do it. But more often than not, in most materials, you'll start getting little dipoles that start aligning with the external magnetic field. When you have a material the little dipole moments that make it up, the atoms inside of it are aligned with the magnetic field, then we have effectively magnetized this material. Now, just like a single dipole will create its own magnetic field, a magnetized material will induce another magnetic field. Just to take a quick example, let's look at what the magnetic field would be for a uniformly magnetized sphere. And due to time constraints, I'm just going to go ahead and show it. Let's see. So here we have our uniform charged, or uniformly magnetized sphere set up in spherical coordinates. And it's going to be rotating as well in this problem. Working it out, and I suggest you do it on your own so it'd be more fulfilling, it turns out that the total magnetic field inside here, which is really just going to be the magnetic field induced by the magnetization, there's no external field here, but it turns out that this induced field is uniform and it's just proportional to the magnetization itself. We're going to use this result in the problem here in a minute. All right. Now, as a moment of convenience, let's discuss the auxiliary field. So in this case here, we're going to have the external magnetic field B naught. It will induce a magnetization, capital M, in this material. And then the material's magnetization itself will then induce a magnetic field inside here, as all the neighboring little dipole moments, their fields point in the same direction and superimpose together. To describe these coupled fields B naught and M, we bring in the auxiliary field H, which is defined. It's 1 over mu naught B minus the magnetization, where this B in this case is the total magnetic field, the magnetization and the external magnetic field put together. This is equation 6.18 in Griffith's book for reference. Let's see. Now typically the magnetization depends on the external field in strange ways, but you know, we're physics majors, we look for the idealized case that's easy to work. What about if the magnetization was simply proportional to the field? And though it's a little weird and just part of convention, it wouldn't be proportional to the external field. We would say, what if the magnetization is proportional to the H field, the auxiliary field? Where this constant here, constant of proportionality, is called the magnetic susceptibility. It's some quantitative, it is a quantitative measure of how easy it is to magnetize a material. All right. Now, running with this, which is equation 6.29 in Griffith's book, we can combine these two, realizing that if I rewrite this top equation, the magnetization is going to be equal to 1 over mu naught B plus H, and then equating these two lines here, we see that this must also equal the susceptibility times H. Now, we put this together, do the algebra, and we end up with equations 630 and 631, where the total field is going to be equal to the permeability of free space plus 1 plus the magnetic susceptibility times the H field, the auxiliary field. Or if we define a new constant, we can simply write B is mu times the H field. Now, this is the permeability of a material, how easy, you can think of it intuitively, though it might not be the exact way to think of it, as how easy the magnetic field or the field lines can flow through a material. And mu naught is going to be just the good old permeability of free space. I guess at this point it'd also be instructive to point out the ratio of mu over mu naught is just 1 plus the magnetic susceptibility here. We'll also be using that in a moment. All right. Now that we got that more or less out of the way, we might as well jump into the problem, which is problem 6.18 in page 277 in Griffith's book. So we have a sphere of magnetic susceptibility, x of n, and it is placed in a uniform external magnetic field B naught. Now, we're tasked with finding what's going to be the field, the new field inside this material, given the fact that this external field will induce a magnetization in here, and the magnetization will then in turn produce its own field inside the material. Now, it's interesting to point out here that there is, within the theory, there's no stopping this back and forth. Starting with the field creating a magnetization, the magnetization creating a new inner field. This inner field coupled with the external field will be stronger still. This stronger new field will then induce another magnetization, and it just goes back and forth and back and forth. And it seems to go back and forth infinitum, which would be a problem with Maxwell's theories. But luckily, we're going to exploit this back and forth to actually answer our question, what is the magnetic field inside here, inside this linear medium, inside this linear sphere? All right, so from the beginning, bringing in this external magnetic field is going to induce an initial magnetization. And if we return to our equation 6.9, or 630, I apologize. If we return to this equation here, then we know that this initial magnetization is going to equal magnetic susceptibility times whatever the initial H field is. But we don't really care what the H field is, we care about the B field. So if we come back here to this equation, we can quickly rewrite H in terms of the total field, this new total, initially the total field for a moment as the magnet, you can think of as the magnetization is being set up, is the external field. So for this first iteration, the initial magnetization is also going to be equal to the susceptibility times 1 over the permeability times the initial field. Plugging in what mu is, we see that the initial magnetization is linear to the initial external field, and we get this constant here. I'm going to go ahead for algebraic simplicity. I'm going to call this constant right here. It doesn't matter. Usually I think the convention is to give constants a k. So all right, so now we have the initial magnetization. Notice that the initial magnetization is uniform. It is directly proportional with the initial magnetic field. And we know from before, we know from the only example I showed you back here, that if we have a uniformly magnetized sphere, then this equation gives us its magnetic field. And this is indeed a uniformly magnetized sphere. So we know that the induced magnetic field, so this is no longer B naught, the induced magnetic field due to this initial magnetization is going to be 2/3 mu naught times the initial magnetization. But we already know that this is proportional to B naught. So the second iteration of the magnetic field increasing is directly proportional to the initial magnetic field. Alrighty. Further down the rabbit hole we must go, because the field B1, this field here, is going to induce another level of magnetization. Again, this B1 isn't its own field. This is B naught coupled with the field that's being created by the magnetization, it's stronger still. The material is going to react to this stronger field and further magnetize. So the second set of magnetization, well, going down the same route of logic, the second set of magnetization M1 is going to be linearly proportional to the second, or I'll just go by iterations, the second iteration auxiliary field. However, we know that the auxiliary field in a linear medium is proportional to the magnetic field. So we continue again, keep our XM, we write in the proportionality of B, let's see, proportionality of B using this equation yet again. And we see that H1 is going to be another set of B1 over mu naught 1 plus the B1 over the permeability, or written out in terms of the permeability of free space, we get this. However, again, we already know what B1 is. We might as well put it in terms of the original field while we're at it. So the second iteration magnetization is going to be XM over mu naught 1 over X sub M. B1 is 2/3 K B naught. Just want to point out here that, again, I'm using the substitution that K is X of M divided by 1 plus X of M. And we see we have another factor of K here. Might as well put the whole thing together. We have 2/3 K squared over mu naught B naught. All right, again, we have a magnetization in a sphere that is uniform. It's directly proportional to the strength of a uniform external field, so it too is uniform, and therefore we can continue and say, well, this guy, this magnetization is going to set up a third iterated field, B sub 2. And this, because it's a uniformly magnetized sphere, has to be 2/3 mu naught times that magnetization that induced it. Well, we already know what the second iteration magnetization is. Let's plug it in. 2/3 mu naught K squared over mu naught B naught. Simplifying things a little bit, we lose a factor of mu naught. I'm missing a factor of 2/3. So this 2/3 comes out of the equation. This 2/3 comes out of the 2/3 contained in B1. So we'll get 2/3 K squared here, and the mu naughts cancel, times the initial magnetic field. So I think you can already start seeing a pattern going on. We're more or less going to get something that looks like the nth iteration is going to be 2/3 K to the nth power with respect to the original magnetic field. Now this sequence term, this smells like a geometric series. It really does. So let's take a look at it. So the total magnetic field, start creating a sum to see if we can get that series to show up. If we do the total magnetic field, well, that's going to be the initial magnetic field plus the first iteration magnetic field induced by the magnetization, and so on, all the way to infinity, because this iteration will go on infinitum, as mentioned before. We're going to get B naught. We already know what We already know what B1 is. Oh, have it here. So we already know what B1 is. This will be plus 2/3 K B naught. And we just found out what B sub 2 is. 2/3 kappa squared B naught. On and on and on. You can quickly see that each of the terms is going to have a factor B naught, so we can factor it out. We're going to be left with a 1, 2/3 K plus 2/3 K squared plus on and on and on. Well, this right here is what I was hoping for, because here we have built a geometric series with infinite terms. So looking in my Schaum's mathematical handbook, the typical series A plus A sub r plus A sub r squared and so on, adding up infinite terms is equal to whatever A is, right? Because you can always just think of this as A1 plus r squared on the way out. So it's equal to A, and divided by 1 minus r. Now this r is the geometric ratio, and this is true so long as the geometric ratio, its magnitude, is less than 1. Well, let's look at what we have here. We have 1 plus 2/3 kappa plus 2/3 kappa squared and on and on. So it seems like our geometric ratio is 2/3 K. And bringing back what 2/3 actually was, because this is just a substitution, this is x of n over 1 plus x of n. Well, 2/3 is of course less than 1, and this ratio has to be less than 1 for any positive value of x of n. And it should be between -1 and 0 for negative values of x of n. So this is of course less than 1. We have a geometric series, or this is our geometric series, and so the total magnetic field, and this is inside the material where the magnetization is, the total magnetic field is going to be our B naught, this is going to be our A, and our geometric ratio is 2/3 K, so we just multiply this by 1 minus 2/3 K. Let's see if we can pretty this up a little bit. Oh, let's just put in what it is. 1 minus 2/3, then we're going to get x of n over x of n plus 1. Ooh, and there's really not much use to simplifying this. So I might as well leave it as that and keep it as our result. And we see that just like a uniformly polarized dielectric sphere, just like a polarized sphere in a uniform electric field, a magnetized sphere in a uniform magnetic field has a total magnetic field that is uniform inside of it. It's just a constant of proportionality times the original field. And there we go. I hope this video was to some extent informative and that this problem, you found this problem as interesting and quaint as I did. Take care.